Hello, it's Keith here, and it's lesson 49 of the platform-specific series of my 6502 assembly programming tutorials, and I have an oscilloscope above me because we're looking at sound again. We're looking at the Commodore PET, and we're going to be writing my ChibiSound Pro driver for the Commodore PET. Now, ChibiSound Pro is an enhanced version of my ChibiSound driver. This one is designed to be potentially capable of music, so we are extending it. The original version was just designed for sort of your classic Atari type of beeps and bloops and noise samples. This one is designed for music. Now the Commodore PET is going to be a little bit tricky for us because it doesn't really support some of the things I was wanting to use. To my knowledge, there's no real way of doing volume levels on the Commodore PET, and noise samples aren't really possible either. So we're not going to be able to do that. We are, however, going to be able to have a sequence of pitches, and we're going to be able to use those to have different notes in the octave, and that will allow us to play some simple music. Now, the ChibiSound Pro driver that I'm writing on all of the systems, let's just get rid of that oscilloscope for a moment. This basically uses 4 different bytes. There's a H byte. Now the bottom 7 bits of this are the channel number. We've only got 1 channel on this system, but we will need to simulate more than 1 if we want the music to play properly. We could just use 1, but we will try and simulate more than 1. We have a volume byte in L, which we're going to ignore, and we have a pitch in DE, a 16-bit pitch. We won't be able to use all of it, but we will use some of it. So that's what we're going to try and do, but we're going to have some limitations because of the capabilities of this system. Now let's just go over to the samples we've got today. So the main sample is the ChibiSound Pro test program here. If I just fire this up, it will get quite noisy, and if we get that oscilloscope back, there's a very loud noise there. So basically, if I find the correct keys on this system, there we go. So as I change, I'm using the joystick simulator keys here, but as I go through the numbers here, you can hear that the pitch changes, and I actually used this to match the pitches to the octave. I used a sort of oscilloscope type program to get the notes frequencies matching. So this is a test here for the general tones, a bit noisy. And then what we've got here is the test for the up-and-coming Chibi Tracks, which is my music playing software that uses the ChibiSound Pro driver. The ChibiSound Pro driver is a hardware abstraction layer. The Chibi Tracks is a multi-platform music software. So the 6502 version, provided there's a ChibiSound Pro driver, will work on any system. And the ChibiSound Pro driver, as you'll see, is pretty straightforward to convert, so hopefully easy to get working on new systems. Now, we've got a transpose option on this system, and that's because there were actually effectively only 4 octaves that we can have on the PET, and that is not as many as ChibiSound is really designed for. So depending on the music, you might want to transpose the octaves. And we've also got a single channel option. Now, as I say, the PET is only really capable of 1 channel. The ChibiSound, the Chibi Tracks was designed for the AY sound chip with 3. And so we've got basically 2 options. Now, the way I've designed Chibi Tracks, the sort of specification states that the first channel is always the most important. So we could simply ignore everything except the first channel, and that will work. You know, we'll get a tune. But what we might want to do instead is we might want to take the loudest of all of the channels. So, for example, if channel 1 is silent but channel 3 is making a sound, we probably want to make the sound that channel 3 making, whereas if channel 1 was very loud, we'd want to make channel 1. If channel 1 was quiet and channel 2 was very loud and channel 3 was silent, we'd want to make the sound of channel 2. And so that's what we're doing here, if I just fire this up here. So this is playing a little tune. It's higher pitched this time because I've had to transpose it, but you can hear it's a little piece of music anyway. And that is supposed to be some sort of drum effects, I think. But as I say, we've got no noise, unfortunately, on this system. Now, alternatively, we can enable the single channel. And now, at the moment, it sounds the same, but I think you'll find those sound effects are missing. Yeah, because those are on channel 3, though. That's the percussion channel, the way I've set it up. So as I say, we've got a couple of choices there, but generally speaking, I think we want to use the virtual channels, which allow for the multiple music channels to play. Now let's take a look just quickly at the hardware and what we're going to have to work with. So basically, there are 3 ports that we need to configure. The port E84B will take a value of 0 or 16, and that will turn the sound on or off. E84A will take an octave number, and each number provides two different octaves, and we can write 15, 51 or 85 to that. And then E848 will take a value roughly from 64 to 255, and that is a tone. Now, depending on the octave we select with E848, this gives us a different set of potential options. Now, if we write 15 to that, we can have octaves 0 or 1. If we write octave 51, then we will have octaves 1 or 2. Now, the octave 1 is the same in both cases. So when we have octave 3 that gives octaves 2 or 3 here, there's basically seems to be some overlap here. And so octave 51, these two options here are basically the same as this octave here and this octave here. And so what I'm going to do is I'm going to basically ignore the value of octave 51, and I'm just going to use octave 15 and octave 85. Now, I'm not aware there's any, if there's a benefit there to this one, I don't know it. Maybe there is, I just don't know it. And then we've got the notes and the correct frequencies to send accordingly. Now the value for the note we have to write to E848. So those are the three ports you're going to see in the code. Now you'll notice at the start of the code here, we have a lookup table. Now this is the relative values that we need to write to the port E848 to select the note. Now these are 16-bit values in the common format for ChibiSound Pro. They're not the native data formats that we would write to the system, because as I say, ChibiSound Pro is designed to be a hardware abstraction layer that allows the music software to control the hardware in the same way on every system, irrespective of what that hardware really does. Now you'll notice that SMS Transpose will effectively skip 2 lines here that we didn't have any notes for, because the frequency range of this hardware didn't support it, and then it pads out the table to make it the correct length with the various highest pitch. And so, as I say, basically I didn't I should probably just let you hear what it sounds like if we disable that transpose and just see that there is a real problem there. Now you can hear that the pitches aren't moving in the correct way. The lower pitches are all the same, because basically the hardware doesn't have enough of a range of notes to do all of the octaves correctly. So anyway, that's our lookup table. And if we want an in-between note, so if we want F sharp, we would just take the F and G values when they're actually filled in, add them to the two together and divide it by 2, and that would give us the correct frequency there. So our lookup table is part of the solution. This is the part that allows music to play, but if we just want sound effects, we don't need to do that. Now, as I say, the hardware itself only has one hardware channel, so we're going to simulate up to 4 virtual channels, and so we're going to define some bytes for those virtual channels. Now the ChibiTrax music player needs 3, but it's easier to work with 4, because then we can take the channel number, which could be 0 to 127, and just take the bottom 2 bits of it. Now what we're going to do is we're going to store the 4 parameter bytes H, L, D and E in that cache. Now technically speaking, we aren't using the volume anyway, so we could have ignored L, but just for completeness we're putting it in there. So we are selecting the virtual channel number here. We're selecting a 4-byte entry in the channel cache, and we're storing it when we use the set command, which we do whenever we want to update the sound. Now, after the channels have been set, though, each iteration, whenever the music is playing, we would want to run the update procedure, and this actually updates the hardware with what the music should be doing. And so this will update the music, and what we're doing here is we're starting off by setting H, which is going to be our volume level, to 0, and then what we're going to do is we're going to scan through each of the entries, and we're going to find the highest value of the volume level. And when we find a volume level that's higher than the current one, which the first one will be, assuming it's not 0, we store the new highest value for all of the entries for that highest value channel number, virtual channel number, in H, L, D and E. Now, once we've scanned the entire sequence, or if we're only using a single channel, we will actually start setting up the hardware with those values. As I say, this means that basically we're supporting up to 4 virtual channels, and we're now only playing the loudest one of those 4 with each update procedure. So what we're going to do here is we're going to take H, which is the volume level of the loudest channel, and we're going to ignore the bottom 4 bits. And if the top 4 bits are greater than 0, we're going to be playing some music. Otherwise, we're going to consider things to be silent, because very low values we probably don't want to play. So say we've got no actual volume level. So if we want to make a sound, we write the value 16 to port E 8.4b. Otherwise we write the value 0, which we would have in there anyway if we get to here. So that's how we're setting our volume. Now what we want to do is we want to select one of our 4 octaves, octave 0, octave 1, octave 2 or octave 3, and so we're going to have a value of 85 or 15. And so what we're going to do is we're going to load X with the value 15, and we're then going to text the top bit of the DE pair. Now this is the frequency level that we want to make, and so if the top bit is a 0, we're going to use the value 15 for octave 0 and 1. If it's 1, then we're going to use the value 85 for octaves 2 or 3. Okay, and we store that octave number into E848, and as I say, we're not using 51 at any point because that, as I say, it seems to be duplicated. So unless there's some difference in the way the sounds are represented, or maybe the volume's slightly different, I'm not quite sure. Anyway, so we're not using that. Now what we're doing then is we're taking the remaining 7 bits of our D entry, and what we're going to do is we're effectively going to multiply that by 1.5 because we need a value from 64 to 255. So we're going to add 64 to make sure it's never below 64, but our 7 bits will only give a value of up to 128. So we need to basically pad that out to give it a value of up to 192. And so what we're doing is we are storing the bits that we want in D, shifting them to the right by 1 bit, and then storing that in B, and then adding the 2 together, effectively, as I say, multiplying them by 1.5. This then gives us the range of values that we need for the octaves. Now once we've calculated that, we store it to E848, which is the channel that sets the note, and that is what we've done there. Now, as I say, all of this sort of comes down to we need to have the correct values to pass to it for the notes we want, and this table here, it was calculated by using a frequency analyzer that told me what note they look like, and that's the one I'm using at the moment. I did try creating an alternative one, which I attempted to calculate in a spreadsheet mathematically. It didn't actually sound as good. I think some of the notes, some of the numeric values written to port E848 give slightly odd results, slightly odd frequencies maybe. I don't quite know what went wrong there, but anyway, as I say, this octave table does seem to be the best one that I've got. Anyway, that is it. Not too complex this time, as I say, because the hardware is quite simple. Now we're going to look in the future at the ChibiTrack software, which is the music player, and I've also got a piece of authoring software called ChibiTracker Pro, which is my music composition software. It sort of mimics Arca's Tracker. It's not particularly amazing, but it does work, so that's what I'm using these days, and hopefully if you're interested in that kind of thing, you will stick around. Anyway, hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.